Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over the value of stability and using it to predict the type of radioactivity that the nucleus or atom is going to go over or go through. So in my last video, I talked about the different kinds of radioactivity, but then the question then comes up is how can we know whether or not a certain atom is going to undergo a beta decay, a positron emission, or an alpha decay, and what's the cause behind it? How can we predict that? So I'm going to get into that into this video. We're going to talk about the value of stability, but first I want to go over a few points that are important to understand why the value of stability is important. The first thing we need to keep in mind is that the nucleus is a collection of positive protons and neutral neutrons. So we know because of the positive protons, we know that like charges are going to repel according to Coulomb's law. So positive charges are like charges. If you have two positive charges, the closer that they get, the higher the potential energy. So again, everything wants to go towards lower potential energy. So if you're bringing two positive charges close together, they're going to want to repel, and so they're going to want to get away from each other. So why is it that the nucleus is not falling apart? You got all these positive protons. Why aren't they repelling each other? What's keeping them together? And what's keeping them together is another force, another fundamental force of the universe called the strong force. And that strong force is what binds all the nucleons together. And so, what we mean by nucleons, again, is all of the subatomic particles that are in the nucleus. That would be the protons and the neutrons. So, both protons and neutrons have this strong force, this attractive force that's holding them together. And this attractive force uh, acts through very, very short distances. So, all nucleons so all nucleons, protons, and neutrons are attracted to each other. So even protons are attracted to each other through the strong force when they are very, very close together. So it acts again. This strong force acts over very short distances. Okay. So there's a balance. There's a balance between the repulsive Coulombic force of the protons, right? The protons want to repel each other, so that Coulombic force, that repulsive force, wants to push them away. But then you've got the attractive force of the strong force of all the nucleons kind of holding it together. So there's this balance of attraction of the strong force and repulsion of the um, of the protons. And so this means that the neutrons then are important for the stability of the nucleus. Why? Because they have that attractive force. So the more neutrons you add, the, that's going to add attractive force and it's going to hold things together. However, you would think that, oh, if we just keep adding more neutrons, then that's going to add more stability and just keeping adding more stability. But that's not the case, right? So it's not the case that if you just keep adding neutrons, that it's just going to become more stable and more stable and more stable. There is a limit. And so why is there this limit? Well, the very interesting thing is that you may not have known is that just like the electrons occupying different energy levels in the atom, neutrons and protons occupy different energy levels in the nucleus. So, as you add more neutrons, right? So, as you add more neutrons, they're going to occupy higher and higher energy levels, right? Remember Aufbau principle, where when you add electrons to the atom, the electrons go from low energy, you fill in the low energy levels first, and then you occupy higher energy levels. Well, in the nucleus, protons and neutrons do the same thing or a similar fashion. Not going to get into it, but that's what goes on in the nucleus. So as you're adding protons and neutrons, or if we're focused on neutrons here, as you're adding neutrons, those neutrons are occupying higher and higher energy levels. And then there becomes a point at which the payoff for the attractive strong force is not going to compensate the high energy state that the neutron is occupying. So if you add more neutrons, those higher energy neutrons are going to have a higher energy, too high. That's going to over how do I should say over affect, if that for lack of a better word, the attractive force that's gained by the strong force. So at some point, the energy for that the neutron occupies is just going to be too high, and the stabilizing effect is not going to be there. So there, and in actuality, there's going to be a destabilizing effect. And so there is an important number that helps us determine the stability of the nucleus. And that number is the ratio of the neutrons over the protons. So remember, Z here, we have Z. Z is the symbol for protons, and N is the symbol for neutrons. So this ratio of neutrons over protons is an important number that we can use to identify the stability or measure the stability of the nucleus. And so that's going to get us into this valley of stability and the prediction of the types of radioactivity. Okay, ladies and gentlemen, so now we're going to get into the valley of stability. So what I have here is a plot. Now, this is not drawn to scale. It's not like perfectly drawn. It's just there for teaching purposes. But you'll be able to find something like this on the internet very easily if you just Google valley of stability or band of stability or island of stability. You'll see a plot of something like this. Now, let me explain what this plot is. This plot here, if you'll notice on the y-axis is N. N is the number of neutrons in the nuclide. And then on the bottom here, I forgot to label it. This is Z. So let me put a Z down there. So Z is the number of protons in the same nuclide. So here, you can plot different isotopes according to the number of neutrons it has and the number of protons it has in the nucleus. And so what is marked out here in orange is where all of the are the isotopes, the plot of where all the isotopes that we have in the known universe that we know today would be in the orange. So all isotopes would be in the orange here. And then in the green is the band or valley of stability. So within this area here would be the plot of those isotopes that have the right ratio of protons and neutrons that allow it to be stable. So what we find here is those isotopes that are stable in this area here. Anything outside the green would be isotopes that are not stable. So you'll notice a few things. So here I have 3 examples. So carbon 12 is down here in the band of stability. So it has a nitrogen to, it has a nitrogen. It has a neutron to proton ratio of 1. So down here, the first 20 elements, stability means you have a neutron to proton ratio of about 1. Once you get past about 20, in order to be stable, the ratio, the neutron to proton ratio has to get higher. So you have to have more neutrons to get stability. So that's why you see the green band starts to go up. This line here, it's straight line. Sorry, didn't have a ruler. So this straight line here represents the 1-to-1 ratio. So you can see at the very first 20 elements, it's about 1-to-1. But as soon as you get past 20, it starts to go up. So stability requires more neutrons in the nuclide compared to protons. And so again, remember the neutrons are adding more strong force, attractive force to hold the nucleus together. So here we have an example of ruthenium. So we have 100. So this is a mass of 100. So it has 44 protons. And so the ratio of neutrons to protons is a little bit more than 1.27, 1.28. And so it's in this area here. And then finally, mercury 201 has 80 protons and about 121 neutrons. So the ratio here is about 1.51 neutrons to protons. And so it's up here somewhere. And so being higher, being heavier, being larger means that you require more and more neutrons in order to reach stability. And so a few things I want to point out here. Again, this green band is where you get the stable isotopes. You'll notice that when you get to a certain point, you don't have stable isotopes anymore. So beyond the protons of 83, beyond Z equals 83, there are no stable nuclei for those elements. So 83 is bismuth. So any element beyond bismuth on the periodic table is not going to have any stable isotopes. So their nuclei are just too big to have a stable, to get stability. So the getting into the prediction of the type of radioactivity, we can predict whether or not what type of radioactivity it's going to undergo. So the type of radioactivity emitted by the nuclide depends in part on this neutron to proton ratio. So what if your neutron to proton ratio is too high? Well, that means that you're going to be above the valley of the stability. You're going to be higher here. So you're going to be up here somewhere, right? Well, how do you get down? That means we're going to have to decrease the ratio. Well, you decrease the ratio by decreasing, where's the ratio? Decreasing the number of neutrons and increasing the number of protons. So that means that you have too many neutrons. Therefore, it has a tendency to undergo beta decay. What does beta decay do? You're taking a neutron and it's breaking apart into a proton and electron. So the beta particle, which is the electron, goes out of the nucleus and you're left with the proton. So you're decreasing, you're changing neutrons to protons. So you're decreasing the neutrons and increasing the protons. Therefore, you're decreasing the ratio. And so therefore, that's going to bring the nuclide closer to the valley of stability. So the new nuclide will be closer to the valley of stability and therefore more stable. What if your neutron to proton ratio is too low? Well, that means you're going to be below the valley of stability. So remember, the valley of stability is the green part, not the orange. So you're going to be down here. And so you're going to have to increase that ratio. And well, how do you do that? That means you have too many protons. And so therefore, you're going to have to convert protons to neutrons. And there's a couple of ways to do that. You can do that by undergoing positron emission, right? So positron emission, the proton releases a positron and what's left is a neutron. And so, okay, so you get a neutron that's gonna increase the number of neutrons and decrease the number of protons. So that's gonna increase the ratio and get you more stable. Or you could also undergo electron capture. So remember, electron capture, so the proton captures an electron and becomes a neutron. So again, you're going to increase the number of neutrons and decrease the number of protons by going through that process. So that's how you can predict what kind of decay your nuclide or your isotope is likely to go through in order to become more stable based on the neutron to proton ratio. So there's a couple of ways you can do this in order to predict what's going to happen with the nucleus. One way is to look at the chart here. Look at your plot, right? If you have a particular isotope, you can figure out what the ratio is, right? You can figure out what the ratio of the isotope is because you know how many protons it has because you know the element symbol, and you know the number of neutrons because you're going to be given the mass, right? The mass number of that particular isotope, and you can figure out the ratio. And then you can figure out, is the ratio within the band of stability? If it is, then you know it's going to be stable. Another way that you can figure out the stability or predict the stability of this of your nuclide of your particular isotope is to compare it to the average atomic mass that you find on the periodic table. So, for example, if you take Ru, ruthenium, Ru has an average atomic mass of 101.07 AMUs. Well, if you have an isotope, let's say the isotope is Ru 112, right? So if that's my particular isotope and I want to know, okay, is this stable or unstable? Well, I can compare the mass of my isotope to the average mass on the periodic table. And the average mass is the average mass of the stable isotopes of all the known isotopes that exist in the nature of this element. And so there's going to be stable isotopes in there. So the most abundant isotopes are going to be the ones that are stable, right? And so we can compare this mass of my isotope, my particular isotope I'm looking at, to the average mass. And I can see here that, well, 112 is much, much larger than the average. So this is telling me that I have way too many neutrons in this particular isotope. This is not going to be stable. It's going to be radioactive. It's going to undergo radioactive decay. And then I can figure out, well, what type is it most likely to undergo, right? What particular radioactivity is it going to undergo in order to lower the number of neutrons? And so what I said before, again, the ratio is too high, so too many neutrons, therefore I can predict that it's undergo beta decay. Okay, so that's it for this video. I hope you found this instructive and interesting. If you learned something, then please, by all means, hit that like button down here, somewhere down here. Also, make sure you subscribe to my channel. Hit that notification bell somewhere up here, or maybe down there. And when you hit that notification bell, make sure you hit all so you get notified by all the videos I put out. Also, put a comment down below in the comment section. Let me know what you think. If you have any questions, I'd love to hear them. Thanks for joining me. Have a great day.